And our first speaker is Simon Davidson from Davidman, sorry. So I should know after all these years. Simon Davidman from Synopsys, but we're ready to go. I'll do the introduction. Our first speaker in this session is Simon Davidman, who is the VP of Engineering, Process Set Modeling and Verification at Synopsys. The title of his talk is RISC-V Processor Verification Requires a Complete Toolbox, which I'm sure he'll explain what that complete toolbox is. He's currently VP of Engineering, as I said, in the Processor Modeling Verification in Synopsys. Simon was a founder and CEO of Impress Software until his acquisition by Synopsys in 2023. Congratulations. And before that was founder and CEO of CodeDesign, automation that created System Verilog from Verilog. I think was also acquired successfully, correct? By Synopsys. There's a trend. In his career, Simon has been involved in 6 successful EDA startups as founder, our first European employee, which has been acquired for over 1 billion in total. We're harking back to Sean's presentation earlier about the amount of money invested and available in our industry these days. Simon has a BSc and MSc in EE from Essex University in the UK. He was a visiting professor at Queen Mary University of London for over 10 years. He has given many conference keynote presentations and numerous papers over the years and has been awarded 5 patents. Okay, thank you.
Thank you very much. Can you hear me okay at the back, right? Okay. So, yes, earlier we had Sean talking about the state of startups and stuff in Europe and the UK, and then Caden's talking about AI. What I'm going to do is focus on RISC-V processor verification. As Synopsys, we also have a presentation later on AI and also on mixed signal. But my focus here is going to be on RISC-V processor verification, which is really where the company that Synopsys acquired 18 months ago, that's what our focus had been for basically a decade almost. I'm going to talk through different things. What RISC-V is being used for, verification is the focus. I'm going to talk about dynamic verification and static formal verification and just introduce some of the topics. So it's quite a technical thing with, and anyone who's seen my presentations before, slides tend to be pretty busy with technical stuff on them, but I think it's been recorded so people can, is that right, Mike? It's been recorded. Yep. Yeah, okay. So focus somewhere else. Okay, so first thing, okay, great. So where and why is RISC-V being used? Well, one of the key things, RISC-V came out of Berkeley 210, I think originally, started being adopted 216. And the key thing is that anybody can build a processor from it. It's a standard ISA, it's well defined, there's a whole ecosystem around it. And you can choose what you include in it, whether you have the initial 47 integer instructions or whether you add all the, the 500 bit minute floating point vectors and everything. You can choose, and it's modular, so you're allowed to add things in and out. But one of the key things it allows you to do is to change the microarchitecture. You define the microarchitecture, and you can define your own instructions, your own custom instructions, your own state and registers and communication in there. So you get complete flexibility, but yet you have an ecosystem that can help you with tool chains and everything like that. So a lot of people have been adopting it from very simple little embedded things through to AI inference engines in there. But what happens is this flexibility gives tremendous challenges in terms of verification. And you get them in several different ways, like from design complexity. You've got to design your own microarchitecture. You've got all these implementation choices you can do in there, and then you've got your own custom features. So that you can have very simple designs, or you can have extremely complex ones. And then you can choose in your system whether you, in terms of a processor, whether you design it yourself, or whether you actually pick up an open source one and extend it and add to it, or whether you actually license one from somebody and then again extend it. So you've got all sorts of choices there, which is a sort of novelty really, because there's some companies focusing on small embedded ones you can license. Some have very sophisticated multi-core application processors you can license. So there's a whole range in there. And then you've got the complexity of there's different use cases. They can be very simple, like a microcontroller, or all the way up to application processors with many cache hierarchy levels, different numbers of hearts, as they call it, the threads in there. And then you can actually choose whether you use just technology internally, which is closed source, or whether you can use open source, whether you want to put Linux on it or your own software and stuff on it. And then you've got the challenges of how you actually verify all of this, and you've got the problems of the productivity of it. And traditionally, processor verification was something that was done in ARM, Intel, and IBM, and Power and stuff. And it wasn't really something that was publicly talked about too much, and there weren't standard products out there. But with RISC-V, if everybody's trying to build their own processors, you have this challenge that you need to do a lot more verification. And then you've got to find engineers who know how to do processor verification. And then there's methodologies, and then there's tools. And hopefully in this presentation, I'm going to talk a little bit about a lot of these different topics. And the key thing is that where we're coming from, and what Mike said, what is this verification toolbox? What's this full toolbox? Was that one of the things that we found with processor verification is you don't just need one thing, you need a whole suite of different technologies in there to help you. And I'm going to try and introduce two different sort of groups of them. One is the formal and the static tools that are used. Now, obviously, from Synopsys, I'm going to talk about the Synopsys ones, but you can see tools from pretty much many of the EDA vendors, but also there's open source solutions out there as well. So I'm going to talk about the formal, but also my background really is more on the dynamic side of things. So I'll probably lean a little bit more on that and introduce several of the different technologies that are used and useful in a methodology in there for processor DV in there. And yes, there's different tools. Maybe I hit the wrong button.
Yeah, I think you escaped from the presentation.
Okay. So, yeah, full toolbox. So, and this lists the main technologies and products that we have from Synopsys in the different areas on the verification from a dynamic point of view, sort of simulation based, and the formal sort of mathematical based. And I'm going to talk through actually pretty much something on each of those things there. And when you're coming to different types of bits of the design and stages, there's different technologies and tools and methodologies that you're going to need in the different places. And this really shows that sometimes dynamic is better and sometimes formal is better in there. For small blocks, when you're doing stuff to do with FPUs, absolutely formal is a much better way to do it. It's very hard with a simulator to cover all the cases, but with analysis, you can do it mathematically. So there's some which are much better for formal, some that are much better for dynamic. When it comes to doing memory hierarchy, there's lots of challenges when it comes to simulation, because you can have to have very large simulations. I mean, we've got one of our customers has 1,000 processors in there, which all have caches and everything. There's a lot to verify there. So a lot of the time you take the small blocks, validate them with a formal tool, and do some analysis in there. I mean, one of the things with when you're doing RISC-V, you can add custom instructions and things, and that's very good. You can use formal to just focus on your instruction to validate that it's doing what you expect when you're doing it in there. I'm going to talk first about dynamic verification in here. So there's really 4 different sections I'm going to cover here. The first is about the Imperius DV technology, that's the name of the product, and the reference model. The second is the methodology that we use in there, which is a lockstep technology. Then talk about functional coverage and how you can measure it, and then talk about test suites in there. So that's from and test generators. That's initial. So talking initially about the DV. So this is a technology that we built in the company that I founded, Imperius DV, and it really came from the work we did in a group which was doing open source processors, and we were working with them, and they were just using our reference model as a comparison technology for their design. And then the next design, they actually were going to have 4 different cores. And we realized we needed to try and formalize the way we were doing things and put it in a structured way so that they could use the verification technology and the reference model with different cores, and came up with an architecture sort of described at the bottom there, where you have the reference model that's inside of verification technology that talks to the RTL. So the RTL, as it runs, traces out information, and then there's a technology in PIRSDB that does an analysis on it. So it's really a front end. It uses the RTL in your simulation. It uses a configurable reference model, and I'll talk a little bit more about that. It does the checking and the scoreboarding for you, so it knows what's happened in there and does it. And it also, there's 2 key technologies that we developed in synchronization. One is to do with memory consistency, which can be a challenge when you have hierarchies of memories or things that are happening out of order with weak memory models that RISC-V allows. And the other is with asynchronous events where you've got interrupts and things going on. And so I'm going to talk a little bit about those in there and dig into those. So one of the key things and one of the key technologies that we developed over basically 15 years was this processor models, and where we take a specification, we study it carefully, and then we hand code a model in there which runs at an instruction accurate level and runs in such a way that the software cannot tell it's not running on hardware. So it has all of the facets of the hardware, just not the detailed cycle breakdown and timing of it. And we've done this model. We initially did it for ARM, proprietary ones, PowerPC, MIPS, and actually we have over 300 different models that we've done from 17 public ISAs, of which RISC-V is just actually one of the latest ones. And a key part of it is that we could build the model and then configure it. And one of the challenges in RISC-V is that it's very, very configurable from which instructions I'm going to have, which registers I'm going to have, but actually which decisions I'm going to make, what priorities I'm going to have to do with different things in my pipeline. So there's lots of challenges that we have to model. And then key thing is you can extend it. So our reference model does that. And our model is used absolutely in verification, but also it's a key component in the Synopsys virtualizer, which is a virtual platform solution for simulating a whole system of processes and behavioral stuff in there. And there's many, many companies use this Empirus FPM as a reference in their bring up and their technology. So what's this lockstep capability? What is this about? Really, it's co-simulation. It's where you have the RTL, the Verilog of your design running next to the reference model, and every time you clock the your RTL, when an instruction retires, you basically check that with this reference model and the synchronization technologies we've got to actually see, do we believe that what you're saying the new state of the RTL is legal from the RISC-V specification? So you can just run any software through it, any behavioral interrupts and timing and debug requests, and we will tell you, are you adhering to the specification or are you deviating from it? So you stop at the point of failure. So you don't run millions of cycles and then realize it failed right at the beginning and stuff like that. So it's very, very sophisticated, but actually, interestingly, sort of works out of the box. And an example of one of the big challenges that people have with DV is that if you get several interrupts happening in one instruction cycle, every hardware is going to do it slightly differently, and sometimes it'll do it differently from instruction. It depends when the interrupt is actually taken and acknowledged by the microarchitecture. And that's a challenge for a reference model, which is basically instruction accurate. So we built this synchronization technology, which carefully checks what's going on. And as you get events and you're told about them, you keep a track of what's going on and checks whether they're legal. And if they're not legal, and we can't find why we think that you've done what you've done, we report what we believe is legal in the scenario, saying this could happen, that could happen, and this could happen, but we didn't see what you've told us you did, which actually finds lots of bugs for people in what they've been doing with their asynchronous stuff. And memory consistency, again, is quite a complicated thing to verify, because if it typically happens when you have multiple threads, multiple hearts or multiple cores and caches in there. And RISC-V has two different memory models. A TSO is sort of what happens in an x86, where you can basically do hardware does most of the consistency of memory, and but the challenge is you have to design quite complex hardware for that, whereas RISC-V has this weak memory order. And the types of challenge that you have there is that you can reorder memory operations, writes can be delayed, certain cores will see values at different times to other cores. So it's very challenging from a verification point of view because of this sort of reordering. And again, we've done a similar thing that we did with the asynchronous in there. We have a mode where you can switch into this weak memory order modeling, and then as it's running, we are keeping check of what's going on, and we have this synchronizer to do this that keeps track of things. And when it finds that something is wrong in there, you then get errors flagged at the point that it's found it. So here, if you look at the right, top right, it says it's detected a memory difference. So this cause read a memory, but actually the RTL thinks it's different from what we've seen. So then we go off and do an analysis of what we think the possible memory values should have been or could have been, and then we report if we find that it's not what we expect or we can't find one that was legal. And we do the same also with instruction fetches, which is actually quite challenging because self-modifying code always has to be flushed properly between different things, otherwise it doesn't work. So it allows you to verify your core with complex things like interrupts and events, and also with different memory hierarchies in there. And when you're running the comparison, one of the things you want to know is how much of it have I tested? So we have functional coverage, and we have technology we've built which we generate from a machine readable specification. We generate actually just hundreds of thousands of lines of system verilog that comes with the technology, so that as you're simulating, you're getting a coverage out of it with the coverage tools in there. We actually auto generate documentation that can be part of test plans and verification plans and things like that as well. So it has a built-in basically functional coverage for all the options that are there. It's sourced so that you can add to it with your own, if you've got your own custom stuff. And we have a technology called Impurus SC for stimulus coverage, which allows you to run test programs with the reference model and system verilog functional coverage before you have the RTL. So if you're starting a project and you're working on the RTL, you can actually start writing your tests and your coverage so that by the time the RTL is ready, you've actually already got the tests and the coverage already up and running, so they can go in parallel. So it allows you to sort of shift left with that, and that just comes with the solution and uses the reference model in there. So you don't need the RTL in there at all. And then next thing is, how do you test this stuff? If that's the verification technology and the coverage, well, we have what we call our TS direct test suites. These are directed tests that we've written. Again, they're auto-generated with templates and an ISA definition. And actually, there's many more test suites than that, about 140 in there. And the same as the system verilog, that's about 400,000 lines of code now, I think. And basically, most of the ISA is very much fixed. An ad does what an ad does. But when you come to the vectors and the memory management and the memory protection, everybody can implement something slightly different and configure it. So we have to generate those suites directly for a customer. So some of it's the same for everybody, and some of it can be customized. And also we can generate custom instructions for people. We did a set for one customer, and we'll generate all those in there. We also have a technology which does test generation, which we license, which is called Sting. And it's a test generation technology that Synopsys we acquired from a company from India, Valtrix, which was very successful. They initially did ARM test generation and then moved again to RISC-V in there. And it's a bare metal technology where you have the ability to define the types of tests you're trying to generate. This is generating you sort of constrained random test streams, so you don't have to direct test them. You choose where you're going. The tests actually can run in simulation with Impurus DV. They can have self-checking technology put into them, and then they can run in an FPGA or in silicon and stuff like that. And they have complete support, like the reference model, of the whole of the RISC-V ratified ISA in there. And again, it does all the complicated things like the memory management and memory protection and things like that. Very sophisticated test generation in there. And the idea is that you can sweep through things and in there. 10 minutes, thank you. So you can sweep through things. So it's not just directed test, it's actually a random test generation there, but it can do all the privilege mode stuff as well, can do multi-heart stuff, multi-core things as well. And you can choose which areas of the instruction set that you're trying to focus on, whether it's to do with memory ordering or floating point or load store units and things like that. So it's a very sophisticated test generator, and it's found lots and lots of bugs for customers. It is really the leading commercial test generator for RISC-V designs. I'm not going to go through the detail. You can pause the video and look at that. We also run not just with the likes of VCS and software simulation, we also have the ability of running verification in acceleration, because you need to do billions of in cycles of simulation and verification. And we have two solutions, one more prototyping HAPS, one more emulation, where you take your design, run your RTL, compile it in, and you can run, at tens of megahertz rather than kilohertz, which is what a software simulator can give you. So we have the ability to perform a lot faster. So that's the dynamic. Let's now switch to the static, the formal. We have a technology called VC Formal, VC for Verification Continuum. And actually it comes with a bunch of apps, we call them, which focus on different bits of the formal challenge, the challenge that's in there. And it's really focused not at a system level or processor level, it's really about unit level in there. And for the RISC-V world, there's a library, the AIP library of the assertion IP, which is a technology that we've built internally, which has assertions for all the different types of instructions and things in RISC-V. And you can use those, and there's a variety of different ways they're used. But for the application, for the assertion stuff, what you do is if you look at a design, there's a picture of a RISC-V down the bottom, you can see there's blocks in the colors there. Those are the types of blocks that you would focus as a unit for the formal verification in there. And here's some examples of it, the prefetch buffer or the decoder, and the types of things that you would do and what you could check with it in there. So you can do things like simple functionality or checking bypass or miss predictions and things like that. And the formal tools allow you to do that. And so you'd feed the assertion library in, the RTL in, and it would do the analysis for you. And it just hooks next to your core with this IP, which is in system Verilog assertions that you connect up and run it. And it allows you to actually get better quality in there and work sort of out of the box. What you do is have to just connect it up with some binding technology, and it allows you to do the analysis on it in there. And there's a variety of different interfaces that can hook into different bits of the pipeline that you're building there. And it's been used internally. It's used in the Synopsys cores that we develop, the RISC-V cores we develop internally, but also there's 4 different open source cores that it's been used with to validate that it's working and that the assertions are correct and everything like that. And again, it's found an awful lot of bugs in there, some which take a while to run, some which would be pretty impossible to find with simulation and take a lot of analysis even with the formal tools. So it's a very good complement to dynamic verification in there. So just to wrap up then, so processors are coming with RISC-V. I think many people are developing them. We have a couple of hundred projects that we're involved in using the technologies that we've got here. So definitely coming. And actually there's several presentations by people here using our technologies in what they're doing. There's a big challenge with processors, with verification. I'd like to say it's a sort of new art form, but it's not really, because it's been around forever with processors. But actually it's sort of only been really publicly required outside the main companies in the last 5-7 years. And we've been building a lot of technology with it. And we actually have other technologies in Synopsys that we've built and that we've actually acquired to help with this. And over the next years, we're going to have a lot of other technologies to help. And it's interesting, as I said, there's a lot of AI technology being developed, and there's another presentation on that. But to be successful with RISC-V verification, processor verification, you need a whole toolbox, and that's really what we're trying to introduce and show you what we've got here. So thanks very much.
Thanks, Simon. Only questions in the room, please. We'll start with questions in the room, and then we'll go to the online ones. Okay, yeah, Surinder, let me come up there with the mic and you can ask a question. Just introduce yourself.
Hello, this is Surinder. I am from Manchester. I have a quick question. You said that the VC Formal, the tool, and then you also detailed about the AIPs which VC Formal supports with regard to Risk V. So I was just wondering that because you have only shown a small set of IPs like Arbiter or LSU or whatever. So is it the only AIP library does you guys support, or there is anything beyond that?
Yeah, I mean, I think the first question is, as I sort of said, alluded to, I'm not the expert in the formal technologies that we have in Synopsys. My focus is on the dynamic side of things. I know that we've got a couple of guys here with our thing here, which will have more information about formal. So I don't really have a specific answer. What this presentation really was about, what we've got in the sort of use for RISC-V in there. And I mean, VC Formal has been around for a long time for different technologies, for different unit tests. And actually, I was at DAC last week, and I saw there was a flow from actually 2 or 3 companies using VC Formal under their agentic AI stuff. So it's very much hooked into that with its APIs and things like that. But I don't know any more details, I'm afraid.
All right, no problems. Thank you.
Thank you.
Thank you, Surinder. Anybody else in the room? I'll go to one of the online ones. Okay. So, how important is a high quality RISC-V reference model for verification, especially if using a variety of verification techniques?
Well, it sounds like I sort of fed that question, seeing I spent the last 20 years building high quality reference models. Yeah, it's extremely important, but actually the quality of the model is absolutely essential, especially for DV. But actually one of the hidden things that's actually very much more important is the ability to configure it, because one model is never going, in a fixed way, is never going to be what everybody needs, because there is so much flexibility in RISC-V, just the implementation choices, like there are with ARM. There's all these implementation choices that you can make at all these different stages. And the quality of the reference model is, you have to be able to have the reference model match what you want. So it has to be designed to be flexible, configurable, and accurate. And I mean, it's interesting, just as an aside, a lot of people build models by trying to invent language to do it and use language. When we realized early on, we do it all with C and APIs, because C gives you tremendous precision and performance. And so we can be absolutely exact of matching what an ARM does, what a RISC-V does, what any RISC-V does. So it's the quality of the reference model is fundamental to the quality of the design you end up with, I think.
Okay. I think we've got 2 minutes left, so time for one more question. Historically, there's been conflict, not collaboration, between dynamic and formal verification technologies applied to SOC verification specifically. Does this still exist, or has it been resolved, would you say, in RISC-V process of verification?
The conflict between formal and dynamic, basically.
Yes, basically.
Yeah, I mean,
conflict may be too strong a word. They're not my words.
I'd say as a simulation guy, when formal came along, absolutely we were in conflict, thinking, no, you don't need any of that stuff, because simulators can do it. But actually, it didn't take long to realize that there are certain problems that simulation is not well suited for. And I tried to allude to that on one of the slides, that it's mathematically hard to compute and test all the different paths, just in simulation to go through all the different paths, whereas mathematically to just analyze it and compute it, you can do it. So there's absolutely areas where formal is far better, and there's areas where dynamic is far better.
Thank you.
So they're very complementary.
Yeah, I refer to my paper of 2000, which was how to mix random, directed, and formal. And typically you start with formal very, very early, because you can get the test bench up and running very, very quickly. That's what we found. And then you slowly switch over to, and there's a very, very good paper from ARM on that, actually, about how you start with formal verification and switch over to simulation. So they complement each other these days. And I'm going to compliment Simon as well for a very, very good talk and introduction to this session. Thank you very much, Simon.